In section 2.5, I'm going to discuss kinematic graphs as related to some of the patterns that we discussed in 2.4. It's very common to see graphs of position, velocity, and acceleration stacked on a common time axis. Because the rate of change in position is velocity and the rate of change in velocity is acceleration, these graphs are all interrelated to each other. And if we're given one of the graphs, we should be able to find the graph shape for the other two graphs. Now, the thing to remember is that when we travel in this direction, traveling down, we are going to relate the graphs through slope. So when we're traveling from the position to the velocity graph, the velocity is equal to the slope of the position versus time graph. And similarly, when we go in this direction, the acceleration is found by taking the slope of the velocity graph. If we choose to go in the other direction, and I don't recommend this because this is the harder way to reason things out. Remember that when we go this direction, we're looking at areas. And when we look at areas, the areas give us the change in the other uh, variable. No, that's not it. In section 2.5, I'm going to discuss the graphs of kinematic values. Oops, sorry. In section 2.5, I'll discuss the kinematic graphs and how they relate to some of the patterns that we discussed in section 2.4. It's very common to see the graphs of position, velocity, and acceleration stacked on a common time axis because when the velocity or acceleration changes, that's going to signal a change in the other two variables. And these graphs are all interrelated. So if you're given one of the graphs, then you should be able to find the shape for the other two graphs. Some things to keep in mind is that when we travel down in the stack, what we're looking to, how we relate the graphs is via slope. So we should remember that the slope of the position graph gives us the value of the velocity. So if we were given a position time graph, we should be able to take the slope of that and infer the shape of the velocity graph. Similarly, if we take the slope of the velocity graph, that's going to determine what the acceleration is. So that allows us to travel in this direction. If we want to travel up in the graph stack, it is a much harder way to reason things out, but it's important. It's an important connection, and when we travel upwards, we're going to take advantage of the area. And remember, the area of a velocity time graph gives us the change in the position. Now, that won't allow us to find the entire graph because the change in position is really just going to give us a family of graphs. So, as an example, let's say that we had an object moving with a constant velocity. Well, a constant velocity, as we move further in the graph, here we might have some area, and then as we move further in the graph, we have more area, and then we move into the graph, we have more area. So, we should be able to infer that we're going to have a straight line. The area is increasing at a constant rate, so the position should increase at a constant rate. And it will look something like this. That'll be the graph shape, but where the graph starts is you can't tell that from the velocity graph. So really all we can tell is the graph shape, and we get a family of graphs. We can only infer the change in the position. So to tell which exact graph we would have if we were given a velocity graph, we would also need to know the initial position, where the object started. Did it start at the origin? Did it start at x equals 1? Or did it start at x equals 2? You can't tell that from the graph. You need a little bit of extra information. This is almost never used, but I'll include it here just for completeness. We can also take the area of the acceleration graph, and that will tell us something about the velocity, but it won't tell us what the velocity is. It will tell us how the velocity changes. In this example, we are asked to find the velocity and acceleration graphs given some position versus time graphs. And the important thing to remember is that as we go down, as we go from a top graph to a graph that is lower in the stack, the thing to look at is the slope. Okay, so as we travel downwards, we're going to consider what the slope of the graph. In this example, we're given some position versus time graphs, and then we need to sketch out what we think the velocity and acceleration graphs are going to look like. So the thing to remember is that we can find the velocity by looking at the slope of the position graph. So for this first position versus time graph, the thing to notice is that it is a straight line, and straight lines have a slope that is constant. Straight lines have constant slope, curving lines have changing slope. Not only is it a constant, it is a positive constant. So we're going to need to graph a constant positive value on the velocity time graph. Well, what's that look like? That looks like a horizontal line. So the graph of an object that is moving with a constant positive slope. On this example, we're given three different position versus time graphs, and we're asked to sketch the velocity and acceleration graphs. So the thing to remember is that we are going to consider the slope of the position graph to find the velocity, and we're going to find the slope of the velocity graph to find the acceleration. We're dealing with slopes here. So for this first one, notice that we have a straight line. A straight line has a slope that is constant. And remember, this slope is what tells us the value of the velocity. So if we have a slope that's constant, that's going to imply that we have a velocity that is constant. Not only is it a constant velocity, it is a constant positive velocity. So we're going to have to graph a constant positive value. Well, what's that look like? That looks like a horizontal line. So a line that looks a sloped position time graph gives us a horizontal line on our velocity time graph. Well, what's the acceleration graph look like? Well, again, we're going to consider the slope of this line. Well, what's the slope of this line? The slope of a horizontal line is 0. So that means that the acceleration is going to be 0. And that should match up with what we've talked about before, since the acceleration is the rate of change in velocity. If the velocity is constant, the velocity does not change, right? The change in the velocity must be 0, and therefore the acceleration has to be 0. So we're going to graph a constant value of 0 for the acceleration for this first family of graphs. For the next one, we're looking at a graph that is curved. Curving lines have a changing slope, so we're not going to have constant velocity here. And when we're looking at the slope, we need to look at what the slope looks like in the beginning of the graph. And the slope in the beginning of the graph looks pretty flat to me. So remember that the velocity is shown with the slope, and the initial slope, and therefore the initial velocity, has to be 0. So our velocity graph, we know, is going to start from the origin. It's going to start from rest. As the graph moves to the right, you should notice that the slope is negative, right? We have a slope and therefore a velocity that is a negative value. And as we continue moving on, that slope becomes steeper and steeper. That means that the velocity is going to become faster and faster, but in the negative direction. And so, what's that going to look like for the velocity graph? Well, that's going to look like a straight line with a negative slope that starts from the origin. So, what about the acceleration graph? Well, again, we're going to look at the slope of the velocity graph. What's this slope look like? Well, the slope here is a negative value. The graph slopes down, and it's a straight line. Straight lines have a constant slope. So remember that the slope here doesn't give us the velocity. This is the velocity graph. This is showing us the acceleration. The acceleration is the slope, and that slope is a negative constant value. What's the graph of a negative constant value look like? It looks like a horizontal line that is beneath the horizontal axis. Okay, for this last graph, this is really two graphs in one. It's really important to point out that we have a section that's right here that appears to be pretty straight. And from here to maybe about here, that looks like the graph is a straight line. And the slope of a straight line is a constant value, and it is a positive constant value. After this point right here, the graph then begins to decrease in steepness. That means that the speed is going to decrease, or another way to say that, the velocity gets closer to zero. And if you look at the graph at the very end, the last data point, that looks pretty flat to me. And a flat graph has a slope of zero. So we know that the end point needs to be a velocity of zero. We know that the initial point needs to be a positive value. And we know that it needs to be a constant value. So we have a horizontal line for the first part of the graph, and then the last part of the graph is going to be a downward sloping line because the velocity approaches zero. For the last graph, we're going to look at the slope. The slope for the first part of the graph is zero. The slope is zero for this first part of the graph, and so that corresponds to a acceleration of zero. For the last part of the graph, we have a negative constant value. So we have a negative constant slope, negative, I'll just put C for constant, and so that will look like that. And usually you'll see these graphs connected with a vertical line. Vertical lines don't really happen in real life, but this is really idealized data, so you can put a vertical line on this. Now for a more challenging example. Here we're given the velocity graphs, and we need to determine the position and acceleration graphs. We'll start off by going downwards in the stack because that's a little bit easier. And we need to remember that the acceleration is equal to the slope of the velocity graph. So considering the slope of this first graph, we should notice that it is a positive constant value. And so we should be able to graph a constant positive acceleration. And that looks like a horizontal line graphed above the horizontal axis. Now, for the position graph, this becomes a little bit trickier. First off, we need to remember that the slope of the position graph is the value of the velocity. So the velocity graph really only gives us information about the slope of the position graph. It can't tell us where to start the graph. We would need to know where the object started its motion or its initial position. And I'll just refer to the initial position as the origin. We'll just guess that it starts from the origin. So looking at the position graph, we should notice that the initial velocity is 0. It starts out from rest. So that means that the slope should start off flat, right, with 0 slope. And as time goes on and the graph moves to the right, the velocity becomes greater. So the graph should become steeper and it becomes more positive. So it should curve upwards in a top opening parabola. It should look something like that. For the next graph, we have a velocity graph that changes its slope from this first part to this second part. So there's going to be a drastic change at this time right here. To look at the first part of the graph, we'll notice that the slope is a positive constant value. And then the slope changes to 0. The graph becomes flat. And so what will that look like on the acceleration graph? Well, we'll start off by drawing a horizontal line above the horizontal axis to indicate a positive constant value. And then we will draw a horizontal line at 0 to indicate 0 acceleration. And we can join them with a vertical line. For the position graph, rather, again, we need to guess at where it's going to start. We'll say that it starts from the origin. Again, the velocity starts from 0, so the graph should start off flat. It should curve upwards because the velocity becomes more positive with time. And so this should curve upwards in a parabola until we get to this point. And at this point, the slope of the velocity graph becomes 0. That doesn't mean that the object is stopping. The velocity is not 0, so the graph should not flatten out. This graph should continue with a positive constant slope because the velocity is a positive constant value. So what's that going to look like? It'll look like a parabola for a little bit until we get to the point where the velocity graph changes its slope, and so this will change its shape. All right, for the last one, we have a velocity graph that is a straight line. Straight lines have constant slope, and the slope of this graph is a negative constant value. And the graph of a negative constant value looks like a horizontal line underneath the horizontal axis. For the position graph, again, we'll have to guess where it starts. We'll guess that it starts at the origin. And we can look at the velocity graph to determine the slope of the position graph. So the initial slope is positive. That means that the slope of the position graph should start off as positive, and then the velocity decreases until this point right here where it reaches a velocity of 0. So at this time, right, at this time right here, the position graph should level out. Okay, the top of a hill or the bottom of a valley has 0 slope, and we refer to spots where this happens as a turning point. Okay, it's where an object reverses direction and stops moving it with positive velocity, and in this case starts moving with negative velocity. So that's going to look like a parabola that curves downwards. And I would also like to point out that at the turning point here, we have a maximum at this point, at the top of a hill. Tops of hills have a slope of 0, and they indicate turning points. All right, these graphs are not something that we're going to work with very often. I do want to mention them. Most of the time we work with kinematic graphs with time on our horizontal axis, but we can also put distance on our horizontal axis. So to determine what shape these graphs should have, I'm going to look at the equation for final velocity as a function of the position. And this is 2a. Normally I put delta x here, but we're going to put d. So I'll write a little note that d is the same as delta x. The distance traveled is the same as the displacement for one-dimensional motion. So what we're going to have, and I'm going to restrict it to an initial speed of 0. What we're going to have if we solve for what's on the vertical axis, we're going to have a square root graph, because the variable that's on our horizontal axis is going to be underneath of a square root, and a square root dependence is going to give us a sideways opening, or a side opening parabola. So what's that going to look like? So if it starts from rest, it'll start from the origin here. That's a speed of 0, and it will look like this. It'll have a side opening parabola. What about slowing down? Well, slowing down is just kind of the reverse of this, where we go in this direction to 0. And I do want to point out something that's kind of interesting here, is that as you get closer to 0, there is bigger changes, right? If we kind of split the graph up into equal-ish divisions, we'll notice that this line right here is way bigger than this line here. The change in a given meter or some sort of distance becomes less and less and less. So as you're speeding up, the biggest change in speed per meter or per foot is going to be the largest in the beginning of the graph. And same thing when you're slowing down. So if you start slowing down, where's the biggest change in speed per distance? It's right here. So when your car is coming to rest and you're braking, your speed is going to start off changing only slightly, and then at the very end, it's going to change very drastically in those last couple of meters, and then even way more drastically in that last couple of inches.